Welcome to part 3 of solving these practice problems for integration. So now we're going to work on some definite integrals. So 11a, we're going to take the definite integral from 9 to 25 of 4 times the square root of w dw. So we're going to integrate 4 times the square root of w with respect to w, and we're going to do this from 9 to 25. Remember what the definite integral is? We're technically looking for the area under the curve for square root of w from 9 to 25. So what I did is I rewrote that. I put the 4 out and I rewrote that as w to the 1/2. Use my power rule, w to the 1/2 plus 1 over 1/2 plus 1. And instead of my constant of integration plus c, I evaluated this definite integral from 9 to 25, which means I'm going to take this function right here, and I'm going to plug in 25, and I'm going to plug in 9, and I'm going to subtract the two values. Now, I simplified this, right? Dividing by 3/2 is the same thing as multiplying by 2/3. 4 times 2/3 is 8/3. And raising w to the 3/2 power is the same thing as the square root of w to the 3rd power. Plug in 25, plug in 9, and simplify, and I end up getting 784 over 3 once I plug in and simplify that answer. Now for b, I'm integrating from 0 to 1 of 5x squared times x cubed plus 2 to the 4th. As you can see, I don't have any product rule for integration, and if I wanted to distribute this out, I would have to take x cubed plus 2 and multiply it to itself 4 times, and I really don't want to do that. So I'm going to try my u substitution here. Remember our rule of thumb, we want to choose whatever is either being raised to a power that has higher powers, that is under a radical, e is being raised to the exponent of e, or in our denominator, and choose that as u and give that a shot. So here I'm going to choose u to be that x cubed plus 2. So when I choose that x cubed plus 2 as u, then my du is going to be 3x squared dx. Well, notice that doesn't match the 5x squared exactly, right? I need a 3 there. So in order to put a 3 there, I need a 1/3. So the 1/3 I don't need and the 5 I don't need. So I pulled those out and I left the 3 inside so that my 3x squared dx would match my du and everything in here would match my u. Now, instead of integrating this in terms of u and then plugging back in x to plug in my original bounds of 0 and 1, I changed the bounds. I changed the bounds from u at 1 and u at 0. So when I plug in u equals u at 0, I get 0 cubed plus 2, which gives me 2. And when I evaluate u at 1, I get 1 cubed plus 2, which gives me 3. So instead of having to go back into terms of x, since this is a definite integral, I can do my u substitution like I did, evaluate my u integral in terms of u like I did here, and change my bounds from 2 to 3, and then just evaluate it in terms of u, plugging in 2 and 3. Evaluated 2 minus evaluated at 3, and I end up with 211 over 3. So now let's look at c. I'm evaluating from 1 to e cubed the integral of 7 over t dt. Now, I cannot bring that t up and give it a negative exponent of -1, because if I did, that would require me to divide by 0. So I need to realize I can pull that 7 out and have 1 over t dt to get the natural log of the absolute value of t. So when I do that, I get 7 times the natural log of t. And instead of plus c, I'm going to evaluate it from 1 to e cubed. Plug in the e cubed, plug in the 1, evaluate, and I get 21. Now look at this one right here. A lot of you may end up taking a problem like this and starting and saying, okay, I'm going to let u substitution, I'm going to let u be 4x to the 5th minus 7x or something to that effect. But notice the bounds. The bounds are going from 3 to 3. The bounds are the same. The area under a curve from A to A or B to B or 3 to 3 is always going to be 0. We have an integration property that says that. Look back in your notes. So you don't actually have to do any work here. It's automatically 0. For f, the integral from 1 to 2, so this one here, again, I don't have a quotient rule. If I let this be my u, that's not a higher power. I'm not going to get that to match. But what I can do is divide each of these by v squared, right? 2v to the 5th plus 3v squared all over v squared. I can divide each of these by v squared. So that's what I did. I divided that first time by v squared and that second term by v squared, and then I evaluated it regularly. And so the antiderivative of 2v to the 3rd is going to be 2v to the 4th over 4, which will reduce to v to the 4th over 2. The antiderivative of 3 will be 3v, and instead of my plus c, I'm going to evaluate it from 1 to 2. Plug in 2, plug in 1, subtract the 2 values, and I get 21/2. For f, here I've got a piecewise function. I'm going f from -4 to 5 of f of x dx. So the problem here is I have two functions. I have the function from -4 to 1 and the function from 1 to 5. So I'm going to have to break this up into two different integrals. And that's what I did here. I said, okay, this is going to be the integral from -4 to 1 plus the integral from 1 to 5. So now I can use the piece of the function from -4 to 1, which is 3. And I can use the piece of the function from 1 to 5, which is 3x squared. And I can separate these integrals and evaluate them separately. So that's going to give me the integral from -4 to 1 of 3 dx plus the integral from 1 to 5 of 3x squared dx. The antiderivative of 3 is 3x. I'll evaluate that from -4 to 1. The antiderivative of 3x squared is x cubed, and I'll evaluate that from 1 to 5. So then plugging in 1, plugging in -4, subtracting those two values, plugging in 5, plugging in 1, subtracting those two values, and I get a final answer of 139. And for G here, if you notice here, we talked about this problem before, this turns out to be part of a circle. This is a semicircle. Look back in your notes. So instead of trying to actually integrate this, we're actually just going to find the area under the curve or under the semicircle from -16 minus x squared all square rooted from -4 to 4. So again, that's half of a circle of radius 4. So I use the circle area, which is pi r squared, but I'm only taking half of it right here, and I get 8 pi. All right, so let's look at number 12. Find the function f of x if its derivative is 2x cubed minus 3x plus 5, and we know that the function evaluated at 1 is 7. All right, so we know its derivative. So we're looking for the antiderivative. So we're integrating 2x cubed minus 3x plus 5 with respect to x. So that is step 1. So I did that here. And I got x to the 4th over 2 minus 3x squared over 2 plus 5x plus c. But what I know is that in the original function, when I plug in 1, I get 7. So this function evaluated at 1 is 7. So when I plug in x equals 1, I get 7. That helps me be able to solve for c. I get c equals 11. Here's my original function. There's the function whose derivative, the exact one function I was looking for, whose derivative is inside that integrand, whose derivative is 2x cubed minus 3x plus 5, who when you plug in 1, you get 7. Number 13, if a ball is thrown off a 200-foot building and the velocity of the ball can be found by -32t plus 18, we can find the height of the ball after 2 seconds. Velocity is the derivative of height. So height is the antiderivative of velocity. So the height is the antiderivative of velocity, which we can find using our integration rules, -16t squared plus 18t plus c. Now we know that the initial height is 200. So when time is 0, when you haven't actually moved the ball at all, the ball is 200 feet above the ground. So when I plug t equals 0 into this original function, I get 200, which gives us that c equals 200. So now that I know what my constant of integration is, that gives me my exact height function here. So now I can find the height of the ball after 2 seconds by plugging 2 into this function here to get 172 feet. For 14 here, we're playing on the rules of integration. Given that the definite integral from 2 to 7 of f of x dx is 11, and the definite integral from 5 to 7 of f of x is 3, we can find the definite integral from 2 to 5 of f of x. Using the fact that the integral from 2 to 7 of f of x is 2 to 5 plus 5 to 7. Well, we know the definite integral from 2 to 5. That's what we're looking for. We know the integral from 2 to 7 is 11. We know the integral from 5 to 7 is 3. So when we subtract 3 from both sides, we get that the integral from 2 to 5 is 8. So let's step it up a notch and let it make it a little bit trickier. Given that the integral from 0 to 3 of x cubed dx is 3, how do we find the integral from 0 to 3 of 5 minus 2x cubed dx? Very similarly, right? Instead of trying to solve this out, we can actually just use this right here. So we can say the integral from 0 to 3 of 5 minus 2x cubed dx is, separate those, it's the integral of the first minus the integral of the second. We can pull the 2 out, and then here, this is information we know. We know that the integral of x cubed from 0 to 3 was 3. We know that this uses one of those properties. It's the rectangle property, 5 times b minus a, and we end up getting 9. Last problem, if the integral from 3 to 13 of f of x dx is equal to 17, and we know from 3 to 9 we get 3, and from 9 to 13 we don't know, but we can find it. But notice I've got a 2 and a 5. Those are different. So I got a little bit of work here. So I'm going from 3 to 13 is going to be from 3 to 9 and 9 to 13. When I solve it this way, since I know this is equal to 17 and this is equal to 3, then I know this is equal to 14. So now playing with my integration laws from 9 to 13 of 2 f of x dx, I can add these two together and pull the 2 out. This right here, this whole thing right here, I know is 14. This uses that rectangle rule, and I can get a final answer of 8. And that is how I solve these integration problems. So I hope this helped you. Please feel free to reach out to me with any questions. I will be available by email, and we will get through this test together. I'm here for you.